Good morning. Today we're going to continue talking about Euler's equation. We're going to apply it to a situation where there's acceleration in two directions simultaneously, so you'll get a little more practice with that. Your next homework assignment includes some additional Euler's equation problems and then also some Bernoulli's equation problems. We're going to discuss Bernoulli's equation in class on Thursday. So that assignment's due a week from today. Any questions about the announcements? Okay, just to review, remember that in Euler's equation what we're saying is when there's some acceleration in the L direction for a fluid that has a given density, then what we can measure is a change in piezometric pressure between 2 points, and the 2 points are in that same direction as the acceleration. And so we simplify things by assuming a linear variation in pressure and apply it between 2 points where we have a pretty important to honor convention on the direction and what we consider as points 2 and point 1 when we're applying Euler's equation. So here's in the x direction. Yesterday I sent an email that had what Euler's equation looks like when you apply it in the z direction. So if there's vertical acceleration, that simply means that acceleration is in z. The distance between the 2 points would be a delta z instead of delta x, but then nothing changes on the left side of the equation. Now that convention for location 2 and location 1 is just that if we're accelerating in the x direction, so horizontally, then 2 would be whichever point is further to the right. If the acceleration is in the vertical plane, then 2 is whichever point is higher than the other. So that's just a review of what you've done so far with the homework assignment you submitted today. Remember that when we had this problem, the pressure change was occurring while the fluid was confined. This tank was closed at the top, and we'll look at a slightly different problem today where the fluid isn't confined, where there's still an acceleration that's occurring, but instead of having a piece of metal at the top that prevents the fluid from sloshing around, if we leave it open at the top, the acceleration doesn't just cause a change in pressure, but it'll also cause a change in the liquid surface elevation. So we'll look at that in just a moment. But remember that essentially Euler's equation is used to predict the response of pressure when there's an acceleration. And the acceleration type is local acceleration. So local acceleration is when there's a change in velocity with respect to time, which we equate with unsteady flow. All right. So let's consider the case of what if we have a pipe and the liquid is going to be flowing from A towards B, but we're interested to know if we want there to be an acceleration. So remember that conditions are unsteady when we're applying Euler's equation, so conditions are changing over time. So there's a certain flow rate through this pipe right now, but it's increasing because a valve is being opened downstream, and we're interested to know what pressure difference between A and B would cause an acceleration of 6 meters per second squared. So this is a little bit different from the previous time that you had acceleration in an enclosed nozzle. You know, we were talking about convective acceleration when there was a nozzle where the diameter was decreasing and that was causing the velocity to go up. Here, this is not an acceleration with respect to position like that previous example with convective acceleration was, but this is acceleration with respect to time. So we're going to look at if Euler's equation can be used to tell us what is the pressure gradient. Pressure gradient is just talking about some change in pressure over a unit length. So rather than seeing exactly how far apart A and B are and starting with some known pressure at one of those points, what we're simply going to do is we're going to find out how much is the pressure changing for every meter of length between the two? All right, so on Euler's equation, we're going to have an acceleration in the x direction. So the way that we expand out Euler's equation will be pressure plus gamma z at location 2 minus pressure plus gamma z at location 1 is equal to negative delta x density and acceleration in x. And again, remember the convention is that 2 is going to be the point that's on the right. So we're going to call B is 2 and A is 1. All right, so that means the pressure at B plus gamma Z at B minus the pressure at A minus gamma ZA is equal to negative delta X density of the fluid, acceleration in X. It says that it's water that's flowing through the pipe, so that's going to tell us the density of the fluid is 1,000 kilograms per cubic meter, and the acceleration, A sub x, is 6 meters per second squared. Now what about the elevations? Horizontal pipe, so ZA is equal to ZB. So ZA equals ZB, which allows us to cancel out both of the elevation-related terms on the left-hand side of the equation. Okay, so what we have is PB minus PA is negative delta X density acceleration in X. And by PA minus PB, what we're really talking about there is the change in pressure. Pressure gradient is delta P divided by some unit length between the 2 points. And so I'm going to move this delta X to the left-hand side of the equation. So now I've got delta X, delta P is divided by delta X, and that's just simply negative density times the acceleration in X. And now we can substitute in the values that we've got. It's going to be negative 1,000 kilograms per cubic meter times 6 meters per second squared. And if we look at the units of what we're going to get, it's going to be negative 6,000, and then the units are kilogram meter per second squared divided by cubic meters. Okay, a kilogram meter per second squared, that's the same thing as a Newton. So it's negative 6,000 newtons per meter cubed, or a Pascal is a Newton per meter squared, right? Pascal is Newton per meter squared. So we can further break this down and say it's negative 6,000 pascals per meter. All right, so negative 6,000 pascals per meter. Do you remember what I said about the direction of acceleration as it relates to pressure change? The rule of thumb with pressure change and acceleration is that the pressure increases in the opposite direction of acceleration. There we go. All right, just so this is recorded into the solution. So in the example, the fluid is accelerating to the right. So if the fluid is accelerating to the right, what that means is that the pressure is going to increase to the left or decrease to the right. So does it make sense that if we have a pipe and the water is accelerating from left to right, we have high pressure on the left and low pressure on the right. I mean, that's what's driving the fluid to accelerate from the left to the right, is just that there is more pressure on the left, and that's kind of the driving force that's causing the acceleration. So the fact that we have a negative sign here, negative 6,000 pascals per meter, that makes sense. You know, if positive x direction is to the right, what this is saying is that there would be a pressure, negative pressure. For every meter to the right that you go, the pressure is decreasing by 6,000 pascals. So if we had dimensions, how far A and B are apart, you know, if they're a meter apart, we'd expect A to be 6,000 pascals higher in pressure than B. If they're 2 meters apart, then it would be 12,000 pascal pressure gradient between A and B. So it's just the rate of change of pressure between these 2 points. Any questions about this one? All right. Well, then with that as a warm-up, let's consider this case where we have a tank of mercury. So note that we're given the specific gravity of this fluid, and with that specific gravity we'll be able to calculate the density and the unit weight. And there's simultaneous acceleration in both the x direction and the z direction, where z is vertical. So the handout I'm giving you right now has this problem broken up into 2 parts. First of all, we want to find the pressure at location F, which means you're going to consider the acceleration in the vertical. And then secondly, we want to find out the unknown distance between G and H, which means you'll have to consider the horizontal acceleration. So the key points here is keep track the correct location 2 versus location 1. Remember, further to the right will be 2, and further above, you know, when you're working the z direction, the one that has the higher elevation will be location 2. And then the other factor is units here. You know, we have pressures defined in kilopascals. You're going to need to change that to either pascals or newtons per meter squared to be able to substitute those pressures into the equation. There's just so many places you can make a mistake on these Euler's equation problems. You can forget to put a negative sign for the acceleration. You can forget the negative sign in the formula. It's easy to switch location 2 versus location 1. There's just so many pitfalls that this is one of those problem types where you really got to double check your work to make sure that you've put everything in correctly. Remember my advice about including the units in the calculations? That also, I think, is important for Euler's because you've got both the unit weight and the density in the same formula. So it'd be easy to mix up and accidentally put like 13,560 where what you really needed was the unit weight. All right, so who got 516.7 kilopascals for the pressure at location F? Good. Now, does that make sense? The pressure at G is 485, and the pressure at F is more than that, doesn't that violate the hydrostatic equation?
Acceleration is going down, so pressure is increasing.
All right, that's right. So it's accelerating down faster than gravity. So if it's accelerating down faster than gravity, then the pressure direction, pressure increases in the opposite direction of acceleration, and the net acceleration here accelerates down faster than it would if it was in free fall with no wind resistance. So the pressure at F is higher, and it should be higher. So it kind of makes sense qualitatively. You should always try and do like a reality check on problems like this. It's another way to look for an error, is just ask yourself, does it make sense the pressure would be greater at F? Is that what we expect? And here, yeah, it should be greater at F because that downward acceleration is greater than G. So we didn't have to put like this acceleration minus 9.81. We don't have to manually correct for gravity when we're working in the z direction, because the left-hand side of Euler's equation is already handling the hydrostatic effect for us. That's what this delta p sub z term is on the left side, and then the right side we just put in the actual physical local acceleration that the body of water is experiencing. Any questions about this first part? Okay, so then what if the unknown is the delta x between the 2 points? We know the acceleration is in the positive right direction. We know the pressure is, let's see, it's higher at G, so that confirms that the acceleration is to the right. Maybe it would be an interesting example if I didn't tell you the direction of acceleration. And you'd have to just look at the difference in pressure and from that infer that the acceleration is to the right. All right, so let me bring up those calculations. So we expand out Euler's equation and substitute h for 2, g for 1, because h is the point that's further to the right, g is the point that's to the left, so it has less x. We're working in the x direction here. So it should be 1.79 meters. Any questions there? Now that you've solved this one in the example, I think that you'll find the remaining Euler's problem on the homework that's due next week to be pretty simple. I mean, it's essentially just the same exact problem. There's not a lot you can do with Euler's problems. Now, let me ask you a question. Why could we not go straight from F to H? You know, we had to work from F to G in the vertical acceleration, and from G to H in the horizontal. But let's say that we knew the what if we were given the delta x? Now, we know it now. It's 1.79 meters. So let me just write that. 1.79 meters is the distance here. And then what was the vertical distance? 0.87 meters? 0.87 meters. All right. So I've told you before, you can't go straight from F to H. What if, all right, we know the pressure at H is 120 kilopascals. What if that's the only pressure that we knew? What if we knew the pressure at H is 120, we know the distance between H and G, and we know the distance between G and F? But we don't know either of the two pressures. What I've told you in the past is, if you want to know the pressure at F, it's a two-step process. First, you have to find the pressure at G, then you can find the pressure at F. But what you can't do is you can't go straight from H to F. Why is that? Why can't we go straight from H to F in this instance, where that's exactly what we did with the tank of gasoline example? If I go back to that to bring up the picture, When I was showing you the solution of this, we could use Euler's equation between T and B. So what's the difference where we were able to go between T and B to find the pressure at B, but now I'm telling you that on this example, you shouldn't go from H to F. That's right. So in this example that's on the whiteboard, there is acceleration in two directions. And so if you tried to find the pressure at F, so let's say, well, there's so many reasons it doesn't work, but let's just say, like what's 1 and what's 2? How would you even know what to choose as 1 and what to choose as 2? Because H is the one that's further to the right, but F is the one that's higher in elevation. And so just even defining what to use as the location 1 and location 2 wouldn't work out. So anyways, the point is that on an exam, most likely I'd try and trick you into like finding some net acceleration. Sometimes students will say, well, 12.5 squared plus 15 squared, and take the square root of that, and that's like the net acceleration. But that method doesn't work. But I'll try and trick you to do it, but don't let me trick you. All right? I'll tell you now, it's a trick. Just go one direction at a time. So you handle the horizontal acceleration, get to a point, and you handle the vertical acceleration. I won't actually tell you to do that. Maybe just one or two of you would be tempted. But anyways. All right, well, let's move on to talk about what if the fluid is not confined by like a piece of metal at the top of the tank. So what we're looking at is some liquid that's in an open tank. It's just atmospheric pressure at the surface. And before acceleration, the liquid level is horizontal. But then when this is accelerating in the x direction, then the liquid level is now higher on the left than it is on the right. And I mean, I think everyone here kind of already understands that. For instance, if you have a glass of water that's really full, you have to walk very carefully not to spill it, right? Have you ever, you can't make a lot of jerking, sudden movements if your liquid is all the way to the top. But if it's all the way to the top, what you have to do is you have to make sure that your acceleration is really slow. Because if you make sudden movements, which is acceleration, what happens is that liquid elevation is going to respond to the acceleration. And Euler's equation can be used to describe the effect of the change in elevation. Because on the inside of Euler's equation is piezometric pressure. And so what it's actually describing is a change of pressure and elevation in response to an acceleration. So both of those things change when the liquid is open. If it is an enclosed tank, then the only thing that's changing is the pressure. But in this case, since it's open to the atmosphere, both the pressure and the elevation are responding to that acceleration. So if we have an acceleration to the right, then the fluid level increases on the left. And that's similar to what I've told you before about the pressure increase is in the opposite direction of acceleration. Remember when we had these enclosed tanks, if the tank is accelerating to the right, the pressure increases to the left. So here, if it's accelerating to the right, the liquid level increases on the left side. So it's kind of the opposite to the direction of the acceleration. So on the bottom of the tank, we no longer have an even pressure. Before acceleration, the pressure on the bottom of the tank was the same on the left as it is on the right. Because we could just apply hydrostatic equation and find out that the pressure at some depth is delta H times gamma. But now, if it's accelerating to the right, there's more depth on the left side than there is on the right. So this is just a horizontal acceleration. It's only accelerating in the x direction, but the pressure is changing as you go in the x direction. Because there's more liquid above the bottom left-hand corner than there is the bottom right-hand corner. The delta H is shallow on the right side, the delta H is deep on the left side. Now the interesting thing about that is that you can use the ratio of acceleration, the horizontal acceleration relative to g, to find out the angle that is made by the new liquid surface versus where it was before the acceleration occurred. So horizontal versus the new liquid surface, you can find that angle alpha, and the tangent of the angle alpha is the ratio of the horizontal acceleration to gravity. So if you have a problem like this, where we've got a tank of water, if you flip over the back side of the paper is where you've got this problem. We've got, now I'll warn you, traditional units. So the tank is filled with water. The overall height of the tank is 7 feet. The length of the tank is 18 feet. And we're given this information that the truck will never accelerate or decelerate more than 8 feet per second squared. So just based on its braking ability and its acceleration capacity, it's never going to accelerate more than 8.02 feet per second squared. So the question is, how high can the liquid level be? Because if it's too close to the surface, then that acceleration would cause it to spill. So we need to have it have enough extra room here so that when it is accelerating, the top left edge is just all the way up to the 7-foot edge of the container. And so we know that g in traditional units is 32.2 feet per second squared, and we're given an acceleration of 8.02 feet per second horizontally. So find out the unknown depth. Essentially, keep in mind this hint, that if it's 18 feet in total length, then the length of this triangle is going to be 9 feet. So that makes this some unknown height parameter. And what we're trying to find is the depth. All right, so if we've got 7 total feet of headspace, then the height above the horizontal that the water rises during the acceleration is going to be 2.24 feet. So that means that of the 7, 2.24 is how much it rose during acceleration. So beneath that, it's going to be 4.76. And so it rises as much on the left as it falls on the right. The overall liquid volume stays the same. So if it goes up 1 foot on the left, it goes down 1 foot on the right. And it pivots about the midpoint of the tank. So 4.76 feet. Okay, so We've talked about local acceleration and convective acceleration. Local acceleration is defined as acceleration is the change in velocity with respect to some change in time. Do you remember what's the formula for convective acceleration?
Change in velocity over the change in position.
That's part of it.
Velocity times velocity gradient.
Okay, the velocity times the velocity gradient. So it's going to be the velocity at some point multiplied by dv dx. Right. So if we're going to draw a little picture of like what kind of a system we'd apply convective acceleration analysis to, maybe it would be a nozzle where the cross-sectional area is either increasing or decreasing. So in this case where it's decreasing, that means you had slow-moving water and then it's fast-moving water, because the same flow rate in terms of liters per second was forced into a smaller cross-sectional area. So that caused the velocity to go up. So velocity changes with respect to position. Whereas the local acceleration, the kind of, if I was going to do a drawing of that, maybe it's like a pipe where we had acceleration over time. I mean, the drawings really don't say a lot. Or maybe, you know, we had an acceleration where we have, it's going in maybe a couple of different directions at once. So just the types of problems we'd apply it would be acceleration is, you know, in this one I think was at 6 meters per second squared, something like that. What flow type is associated with local acceleration?
Unsteady.
Good, unsteady, that's right. So unsteady is what we say when it's changing over time. And then what is it when the flow is changing with respect to position?
Non-uniform.
Non-uniform, right. I guess we could call it ununiform, but they just call it non-uniform. I don't know why. All right. Euler's equation is used when we have local acceleration. So use Euler's. Okay, you use Euler's equation if you've got a local acceleration. What do you use it for? What relationship does Euler's equation define?
How the pressure between 2 points changes with the acceleration.
Good. So to predict delta P between 2 points, and that's how you'll mostly use it, but it's not just the delta P. It also defines the change in elevation. So I guess more specifically, we'd say the delta P sub z, because inside Euler's equation is P plus gamma z. So it's also talking about how the liquid level responds to that local acceleration. So you use Euler's equation to predict the change in piezometric pressure between 2 points. When we get together on Thursday, what we're going to start discussing is an equation that tells you how does the pressure change when there is non-uniform flow caused by convective acceleration. And so for that, you're going to use Bernoulli's to predict, same thing, the delta P. So acceleration causes changes in pressure that are different than the hydrostatic equation. That was like your first equation that predicted change in pressure. If the fluid's not moving, if it's not accelerating, then hydrostatic equation will work just fine. But it can be either accelerating, the fluid can be accelerating with respect to time, with respect to position, and then later on we're also going to look at just the special case of what if there's centripetal acceleration. What if the fluid is going in a circle, irrotational flow? And so that'll be maybe a third kind of acceleration that we'll consider as a special case. That's the overview of why we're handling this, kind of the theoretical background of where Euler's fits into the types of accelerations that we've been talking about. Let's look at the announcements before I let you go. The homework assignment is due on Tuesday, but since Euler's equation is fresh in your mind, I'd encourage you to get an early start on that. It'll take less time if you do it today than if you do it Monday night. So if you have any questions, let me know, and I'll see you on Thursday.